Okay, so now this lesson is about the last scenario, the very last scenario in a discussion of exponential smoothing. So now the only difference between the second and the third scenarios, this time we have seasonality added to our data. So the trend is either increasing or decreasing, plus we have seasonality. Moving on. Such data, let's consider a sales data, sales for the souvenir shop at a beach resort in Australia. Rob Heinman is from Australia. So he got the data from a souvenir shop, the sales data. And that data is available in this URL. You can download it and play around with it whenever you get a chance. Now, here's the data. First thing to note is that I'll start off with the log of the data. Why? Because we are already familiar with the fact that sales data is seasonal and it's multiplicative. So if we take the log of the sales data, it will be additive. An essential feature for our algorithms to work is that the data should be additive. We need additive data for our algorithms to work. So we start off with the log of souvenir time series. And how does the data look like? Now this data is additive. The fluctuations are roughly the same across time. So it's no more multiplicative because it's the log. And you do see a trend. It goes up and up. Sales over the years goes up and up. The sales dollars. That's also pretty much common sense. But at the same time, it does show seasonality, right? It rises and falls at the same time of every year. So it does show seasonality. So those are the key features of the data that needs to be observed. So what all did you do in R? You first read in the data, converted it into time series, you plotted it, you saw that it's seasonal and multiplicative. So you took the log, you log transformed it. And here we are having a look at the log transform data. So now moving on, so we are going to deal with the log transform data. We are going to feed Holt-Winters the log transform series. And do you notice something in this call of the function? Well, we have not mentioned anything about the alpha, beta or gamma. And why is that? Well, in the previous calls of Holt-Winters function, say first smoothing the series. In the second scenario, we said gamma equal to false. In the first scenario, we said beta and gamma false. And again, let's shoot back to a discussion of the three types of exponential smoothing. So here's the last scenario of exponential smoothing, the triple exponential smoothing, where we added in seasonality. So here, going through it once more quickly, you see three equations. The first to smoothen the level, the second to smoothen the trend, and the third to smoothen the seasonality. And each requires a different smoothing factor. The first one alpha, the second one beta, and the third one gamma. So for single exponential smoothing, when we are doing it in R, so when we are doing the single exponential smoothing, we didn't need beta and gamma. We said beta equal to false, gamma equal to false. For double exponential smoothing, we don't need gamma. We just need alpha and beta. So we said gamma equal to false. Alpha smoothened the level and beta smoothened the trend. We didn't need gamma for the second scenario. And for the third, we need all three of them. So we are not setting any of those smoothing parameters to false. So that's a point to be noted. However, apart from that, if you set those options correctly, Holt-Winters knows which kind of exponential smoothing to do. If you don't set any of the alpha, beta or gamma to false, it knows it should triply exponentially smoothen the data, and that's what it does, and stores it in this forecast vector. Now, of course, print out the output from the forecast vector. You see and note the three smoothing factors. Holt-Winters function has come up with an alpha of 0.4, which is close to 0, but not quite close. So what that says is that it's placing importance both on the recent data as well as the older data. It's not placing importance just on the more recent data. It's placing importance on both. And that relates to the smoothing of the random fluctuations. It sets beta equal to 0. So the trend, for smoothing the trend, it just places importance on the older time or older time points, not the more recent one. And gamma is almost close to 1, which basically says that it is smoothing the seasonality factor by weighing the most recent seasonality component most importantly. So this is how you can interpret the three smoothing factors, but for practical purposes, when you are doing it in R, you leave it to Holt-Winter's function to come out with the smoothing, and later on we'll check the autocorrelations of the residuals. If the autocorrelations of the residuals look good, that is if the residuals do not look autocorrelated, and we are going to find that out by plotting the autocorrelations via the ACF function and also by doing the Jones box test. If those tell us that the residuals are not autocorrelated, we are in good shape. Like, we do not need to smoothen any further. What the Holt-Winter's function has done is good enough. So now that we have the in-time forecasts, just remember from the older discussions, previous discussions, that Holt-Winter's will just give you the in-time forecasts. And if you plot the in-time forecasts, here you see two plots. You can definitely make out two plots. One's a black one, this guy, and the other one's the red one. The red one is the forecast. And a quick look at it tells you that the red one is overlapping the black one. It's varying the same way as the forecasts are varying the same way as the actual data. So of course our in-time forecasts are validated. They look good. Next thing to look at is the SSE, the sum of squared errors from the in-time forecasts. So that again gives you a measure of the accuracy of the in-time forecasts. But the plot is a visually and more conclusive thing to look at. Next, we want to forecast for the out of time period. We forecasted for 48 out of time periods and store it in the forecast 2 vector. We move on to plot the out of time forecasts, and here again we have the actual data in the black and the forecasted out of time forecasts in the blue. So the out of time forecasts in the blue show the same change in trend. It goes up and up, and same seasonality, that it rises and falls the same time of the year as the actual data. So the out of time forecasts resemble the actual data. Again, the orange part gives us the 85% confidence, the yellow part gives us the 95% confidence level, and you can actually look at the data by printing out this vector's fitted variable, the fitted variable associated with this vector. You can have a look at the data forecasted by Holt-Winters. So out of time forecast looks good. It's in the same ballpark and shows the same pattern as the actual data. Moving on, we plot the autocorrelations for a lag of 20. Here we do not see any significant spike. None of the spikes other than the spike at lag 0, it goes above or below the blue line at the top or the bottom. So we do not see any significant spike at all. So the autocorrelations look good. The residuals are not autocorrelated. We confirm that by the Jones box test. We look at the p-value. The p-value is not significant. The p-value tells us that the test statistic is not significant. The p-value is higher than 0.05. So the plot, the previous autocorrelation plot combined with the box test definitely tells us that the residuals are not autocorrelated, so we do not need to smoothen any further. Next, we simply plot out the residuals. Yeah, of course, they look randomly distributed and perhaps with a mean of 0. And last but not the least, we plot the histogram of the residuals, and that conclusively tells us that the mean of the residuals is 0 and there are equal number of positive and negative error terms on either side of the mean. So the ACF plot, the box test, and the residual histogram combined conclusively tells us that the residuals are not autocorrelated. We have smoothed enough. Our model looks good. From a validation perspective, the plot of the in-time forecasts overlap with the actual data, and shows the same pattern. So the in-time forecasts look good, and then the plot of the out-of-time forecast also shows the same pattern as the actual data, and in the pretty much the same ballpark. It shows the same trend. It goes up and down pretty much at the same rate, and also the forecasts show the same seasonal patterns, like it goes up and down at the specific time of the year. So the out-of-time forecasts also look pretty much same as the actual data, and hence we are good to go. We can conclude that Holt-Winters function has triply exponentially smoothed the data and forecasted with a fair amount of accuracy, with reasonable accuracy, and we can use these forecasts to take a decisions. Now let's move on. Let's wrap up this lesson by discussing about the automatic function that R has to do the R exponential smoothing. And it's automatic because we'll just blindly trust this function, that's the ETS function. We're going to check the accuracy of the forecasts, and that's the only thing perhaps we need to do. We won't need to do all the steps like checking the autocorrelations or checking the residual plots, etc. If you want to avoid that, you just want to use the ETS function. So the ETS function, straight shot, can smooth in both the trend or seasonal part of your time series. Now you can split your data, you should split your data into a training and a test set, and use the training set to feed in your training data to ETS to build a model, and then you can use that model to forecast for your desired number of time periods. Like here we are trying to forecast for 12 future time periods. Use the forecast function to forecast on the basis of the model that you have acquired from the ETS function, and this gives you the forecasts. Now fit vector contains your model from the training set. You can print out the output from the model, and this gives you all the three parameters for the level, the trend, and the seasonality, and you can see how those smoothing parameters look like, and that will tell you whether it's doing a good job. Like remember, while trying to do a forecast for the hem diameters, we used an experience about the data that the hem diameters in modern times are never going to be as large as before, and Holt-Winters used a smoothing factor beta close to 1, and that basically tells us that Holt-Winters is trying to lay more importance on the more recent data, which sounded totally reasonable. So you know the data, so you can look at the alpha, beta, and gamma from the ETS function and use your expert common sense to judge if it's doing a good job or not. And then we can move on to actually validate the model using a test data. So we can use a function accuracy, which prints out a whole bunch of statistics related to accuracy. So in FCAST we had the forecast for 12 periods. So we can take the test data, the actual data for those 12 periods, and test our forecast against that actual data. So the test data is beyond the training data, and we tried to forecast it using our model, and then we are trying to compare our forecasts against the test data to see how accurate accurately it performs. If it performs accurately, we can go beyond this, or we can use it next time just to do our forecasts and totally blindly rely on ETS. So this is something, this testing, validating against test data is something you cannot do using Holt-Winters function. These are like specialities of R, or things of R that you need to keep in mind. You can't do this with Holt-Winters. So this ETS function kind of makes it automatic. You can write code to train it, to use the ETS function to train with the trained data and find a model, then use the model to forecast for the next desired number of time points, and then validate your model, that is this FCAST vector, against your test data and spit out a whole bunch of accuracy to check whether it's performing well or not. So that is the way ETS function differs from Holt-Winters, and it's good to know about this function because your task might require to build your model really quick or build multiple number of models at one shot. Then perhaps you'd prefer to use ETS as opposed to Holt-Winters. That said, we can wrap up our exponential smoothing section, and the stuff we learned is that there are two functions in R, one is Holt-Winters, one is ETS. When you do exponential smoothing with Holt-Winters, there may be three scenarios. First one, in which there will not be any trend. The data will be totally random, and that will look like our first data, that is this data. And if it's totally random, we just need to smoothen the random fluctuations. We just need to use alpha for the smoothing factor. When we are using Holt-Winters, we'll set beta and gamma to false. Second scenario, there is trend. So there is some rise or fall of the data with time, as in our hem diameter example. So in that case, when we use Holt-Winters, we need both alpha and beta, alpha to smoothen the level and beta to smoothen the trend. We'll set gamma to false. And third scenario is when there's both trend, that is the data is rising up and up, and seasonality, there's periodic or cyclical rise and fall of the data at the same point of the year. Then we use Holt-Winters, and we need all the three smoothing factors, alpha, beta and gamma. Alpha for level, gamma for beta for trend, and gamma for seasonality. We would use Holt-Winters to get a model, and that will be an in-time forecast. We can look at the alpha, beta and gamma and judge according to the nature of the data whether those alpha, beta and gamma sound reasonable. Then we can plot the in-time forecasts against the actual data to see if they're in the same ballpark. If they are, in-time forecasts are validated. Next, we forecast out of time, that is beyond the actual data, plot the out of time forecast and see if the pattern and the magnitude of the out of time forecasts in the same ballpark as the actual data. If it is, the out of time forecasts look good. And the next three things we do is to plot the autocorrelations. To plot the autocorrelations of the residuals. If there is no significant spike in the autocorrelation plot, then there is no autocorrelation. We confirm that by performing the box test. If the p-value is from the box test is higher than 0.05, then the autocorrelations between the residuals is not significant. And lastly, to just confirm, we plot all the residuals to see if they're randomly distributed. And the final step is to plot a histogram to see that the residuals have a mean of 0 and they're equally spread and they overlap with a bell curve. So those are the steps if you're using the Holt-Winters function. With ETS, you split your data into train and test, build a model using the train, and forecast using the model you have built. And then moving on, like you can look at the alpha, beta and gamma parameters to see if ETS is doing what it should do depending on the nature of the data. And lastly, you can validate the forecasts against the test data and print out these matrices for accuracy. We are going to have a closer look at those matrices in a validation section. And that pretty much wraps up our exponential smoothing section. and we are going to move on in the next lesson to perform a Riemann in R.